Hello and welcome to Bedroom Physics. This is the example video for application of Newton's laws, and I'm going to be doing two problems, one which involves solving for the coefficient of friction, and the other one which involves using friction to solve for the acceleration of the system. Now for this problem, where we're solving for the coefficient of friction, we have a ramp and it's slanted at theta is equal to 36.9 degrees. We have mass A under mass B. Mass A is sliding down the ramp at a constant velocity, meaning that the acceleration is going to be equal to 0. The weight of A is 9W, so it's going to be symbolic, and the weight of B is going to be 3W. And the friction, or should I say the coefficient of friction between surfaces C and A is equal to the coefficient of friction between surfaces A and B. And I'm going to be using the symbol mu interchangeably to indicate that value since they are equal to each other. So the first thing that we probably want to do is find the normal force that C is exerting on A. And since there are two masses, right, exerting forces on the surface, the force that the surface is going to exert on A is going to be equal to the two masses, or the forces from the two masses. So basically, if we think of this coordinate plane, on the y-axis or the negative y-axis, we're going to have the superposition of the two forces, or just the total weight. And that's going to be equal to 12W. But the normal force is actually perpendicular to the surface, right? So we're going to have to do some vector math here and kind of change the coordinate plane to this, right? Now, if we want to find the force that's perpendicular and down on the ramp, we pretty much just draw a triangle, right? Because this tan line is made from the components, okay? And this is going to be the y component, and this is going to be the x component, and I'll show you why. It's interchangeable, but I'm showing you why I'm treating it that way. So we know that if this is theta, this makes a right triangle here, which means that this angle here is 90 degrees minus theta, but I'll just call that phi. Now the angle between the ramp and this perpendicular line is obviously, since the perpendicular is 90 degrees. And since we already know one angle, which is phi, and phi is 90 degrees minus theta, then this angle has to be theta. And if you have it in this arrangement, then this vector is going to be equal to 12W cosine theta. And this vector is going to be 12W sine theta. And this means that the normal force is 12 on A is 12W cosine theta, which means that the friction force between mass A and surface C is going to be equal to 12W cosine theta mu. Now there's also friction force between A and B. And pretty much this coefficient of friction between the two surfaces are interchangeable. So if we treat A as the surface with the coefficient of friction, B exerts a downward force on A, which is going to be equal to, well, since B is straight downwards with 3W, then when we make the triangle here, it's going to be the same situation, 3W cosine theta and 3W sine theta, which means that the friction force from A and B is going to be 3W cosine theta mu. Now, A specifically is traveling downwards at 9W. Because B is not traveling downwards parallel to the ramp. It's being held by this rope. So if we did the triangle for A, it would look a little something like this. So this is 9W. This is 9W cosine theta. And this is 9W sine theta. And that's all the forces in the system. So when we do the math, the sum of the forces parallel to the ramp, which we're going to call f of x, which is equal to 0, since, again, the velocity of A is constant, acceleration 0, acceleration times mass when acceleration is 0, 0, obviously, is going to be equal to 9W sine theta, which we're actually going to make negative. I'm going to say the left is negative and the right is positive, plus 3W cosine theta mu plus 12W cosine theta mu. We're going to move over 9W sine theta. We're going to have 9W sine theta. And I'm also going to separate the u is equal to mu 3W cosine theta plus 12W cosine theta is 15W cosine theta. Dividing over, we're going to get 9 over 15, which is 3 over 5, and sine over cosine is tangent, and W over W is 1. So we're going to get 3/5 tan theta is equal to mu. Now theta is 36.9 degrees. The tan of 36.9 degrees, and 3 times 3/5 is going to be equal to, I think, roughly 0.45. So that's going to be the coefficient of friction for both the surfaces A and C and A and B. On to the next problem. Okay, so the next problem, we have mass A, B, and C. They're connected together with massless rope. C is descending downwards at a constant velocity, and we know what that means from the previous problem. We have B and C are on a ramp, and its angle is at 36.9 degrees. And the coefficient of friction between A and the surface and B and the surface is 0.35, and both the weights of A and B are 25 newtons. What you want to find is the tension in the rope connecting A and B. We want to find the weight of C, and we want to find the acceleration of C if the tension of the rope between A and B was equal to 0. In other words, if you cut the rope, what would be the acceleration of C? So the first thing that we're probably going to want to do is, make free body diagrams. Now, one important key thing about this problem that we're doing is that C is descending downwards at a constant velocity, right? So if C descends, that means that the masses are moving upwards. So now we know which way the force of friction is going to be, right? So the force of friction for A, FA, okay, and that's going to be equal to, if this is WA, this is N, and force of friction A is going to be N mu. Now let's look at mass B. We know that the force of friction for B is going to be going this direction. So first we need to find the known force for B. We know that the weight down is 25 newtons, which means that when we do the components here, this perpendicular force is going to be 25 newtons cosine theta, which gives us our N. And of course, this is weight C. First things first, how do we find the tension for the rope that's connecting A and B? Well, if we have a force of friction to the left, okay, then our tension is going to be to the right. The addition of the force of friction and the tension need to be zero because this entire system is in equilibrium. Right? So the sum of the forces for this specific part, so we'll call this F1, which is equal to 0 since the system is in equilibrium, is negative FA, I'm treating the left side as negative, plus tension AB. Meaning that tension AB is equal to F of A. Okay? Now let's look at the system as a whole. We found T of A, B, now we want the weight of C. And of course, I haven't solved for this numerically yet. But okay, well, let's just solve for it numerically. This is equal to 25 newtons times 0.35, and I think it's like 8.75 newtons. I'm pretty sure that's what it is. Okay, now let's look at the entire system. So force, which is equal to 0, and this is going to be the force. Let's do, I mean, technically this is all horizontally, but the pulleys are kind of changing directions. So I'm just going to call it F of X though. So to the left, we have F of A, right? And we also have, and these are going to be negative, this is FB. And we also have the force of gravity on B, right, which is going to be 25 newtons sine theta, right, because this right here, 25 newtons sine theta, plus the weight of C, right? It's going down, but it's just that because the pulley's changing the direction, but we're basically going to the right if we're looking at it from a horizontal perspective. So the weight of C is going to be F of A plus F of B plus 25 newtons times sine of 36.9 degrees, which is going to be equal to approximately 30.8 newtons, right? And oh yeah, I forgot to mention, F of B, of course, is 25 newtons cosine theta mu. Okay, so now we have the weight of C. Now let's cut the rope between A and B. So our new system is just B, C, WC. If we're cutting off the piece, then, and it was previously in equilibrium, then we can kind of assume that there's going to be acceleration downwards, which means that the force of friction for B is going to be to the left. And of course, again, we have 25 newtons sine theta. And this time, our sum of the forces is not going to be equal to 0. Let's set it equal to MA. And M is going to be the sum of the two masses, right? Since the rope is massless, this is all one system. And that's going to be equal to negative FB minus the weight of gravity downwards, 25 newtons sine theta, plus WC. Okay? Now we're going to divide the masses over. And A is going to be equal to negative FB minus 25 newtons sine theta plus WC over, now we don't have the masses, but we can solve for it, right? So we get weight by doing mass times acceleration. The weight downwards is mass times the acceleration of gravity. So we're going to have 25 newtons, which is the weight of the box B, over 9.8 meters per second squared, plus the weight of C was 30.8 newtons over 9.8 meters per second squared. And if we plug that into a calculator, we're going to get 1.54 meters per second squared. And of course, FB is that. And that is, we have solved everything this problem is asking for. This has been the example video for application of Newton's laws. Hope to see you in the next concept video.